Hello dear student, this is Dr. Aisha Nazuk here. Welcome back to this channel, Rao Hub. As you know, my regular viewer know well that I am a faculty member at National University of Science and Technology, that is NUST in Pakistan. And I have a PhD in statistics, and I keep using this channel to share the knowledge, my humble knowledge that I have with my dear viewers. On this channel we have different type of playlists. For example, one of our playlists is on introduction to statistics. I have two playlists on econometrics. One of them is on introductory econometrics, which by the way is this playlist. And then I have a playlist on applied econometrics as well, where we discuss aspects of econometrics in reference to the Stata software. I have a playlist on different tips related to statistical softwares such as SPSS, Excel or Stata. Then interestingly, this is a holistic learning experience. This channel also have a playlist on positivity and human behavior, and quite interestingly I also have a playlist on the genre of humor. So thank you for watching, thank you for supporting my channel. It's a humble request, keep sharing my videos, please subscribe to my channel, and turn your notifications on, so whenever I post a video my dear viewers have an idea that there is something new on the channel. Okay, so without further ado, let's start chapter number 10 of Gujarati and Porter Book. Those of you who have been watching the previous videos in this playlist, they are well aware of the fact that I use Gujarati and Porter Book to acquaint you with the basic concepts of econometrics. So far we have covered 9 chapters, and today we are going to cover chapter number 10. If you want to watch a video on how to download books from the Genesis library, which is an online repository to download different books, you can watch my video where I have covered or I have taught the viewers how to download free books. So chapter 10 is about multicollinearity. Actually we are once we study different assumptions of the OLS or CLRM, that is ordinary least square or classical linear regression model, we discussed a set of assumptions that under which assumption a typical OLS performs well. So one by one we are relaxing those assumptions, and we will see what are the consequences. So first of all, we are relaxing the assumption of no multicollinearity. As the name suggests, multicollinearity means dependence among different variables. So remember that when we have a multiple regression model, we have more than one independent variables in the model or the regressors. So the assumption, according to the assumption of no multicollinearity, the regressors should be independent of each other. In other words, the independent variables should not be correlating. So we will discuss in detail what is the nature of multicollinearity, and how multicollinearity can pose a challenge for the interpretation of OLS results, what are its consequences, how can we detect it, and what are the remedial measures that we can adopt to alleviate the problem of multicollinearity. So these are the contents of today's lecture. As we said that multicollinearity means dependence or correlation between the independent variable. By the way, the term multicollinearity was coined by the Norwegian economist Ragnar Frisch, and it was way back in 1968. So he coined this term, and by the term multicollinearity, what he originally meant that there is a perfect or exact linear relationship among the explanatory variables or the independent variables. For example, if we have this type of an expression, lambda 1 x1 plus lambda 2 x2 so on till lambda k xk, where all lambdas, these are some constants, whereas these x1 x2 so on till xk are the independent variables. So you can easily see that I can write this equation in a form that one of the variable, for example x1, can be written as a linear function of the remaining variables in the model or in the equation. So that means that this expression is an illustration or an exhibit of perfect multicollinearity. Nowadays, the term multicollinearity is used in a much broader sense. I mean, it's not necessarily limited to the case of perfect multicollinearity as depicted in equation 10.1.1. Nowadays, it's also, multicollinearity is also defined as a high correlation between the independent variables. For example, if you look at the equation 10.1.2, now you can see that we have introduced a term vi, which is something you can say unpredictable or the random error term. So now even if I rearrange this equation and suppose I want to write the value of x1 in terms of the remaining variables, as I have done here. By the way, here I solved it for x2. So for the case of the perfect multicollinearity, you can see that x2 may be written as an exact linear expression of other variables, whereas if we have the random error term in the model, that is the second equation here, so if I try to isolate x2, then x2 is a function of x1, x3 so on. Still as the first these k terms, first k terms, these are all linear, but we have this additional term here vi over lambda 2. So it is a linear combination, but not an exact linear combination of only the x variables. We have an additional term here which is from which is other than the x variables. So this is the issue. This is a depiction of multicollinearity, whereas equation 10.1.3 is a depiction of perfect multicollinearity. Okay, so now we will also discuss an Excel sheet where I'll show you what is meant by perfect multicollinearity versus strong multicollinearity. So let me open this sheet here. Okay, yeah. So let's say we have this data here, x2, x3 and x3 star. Suppose that I make a scatter plot of x3 with x2. So by the way, I have already done that here. So you can see that when I plot x3 versus x2, all the points, they are lying exactly on the straight line. So that means x3 and x2, they have perfect correlation among themselves. So even if I calculate the correlation between x2 and x3, that I have done here by using the correlation function of Excel. So if I calculated the correlation between column A and column B, which is x3 and x2, the correlation comes out to be 1. So both the scatter plot and the statistical value of correlation is telling us that there is a perfect correlation between x2 and x3. So if we introduce x2 and x3 as an independent variable in same regression equation, then we are committing or we are facing the issue of perfect multicollinearity. Now consider x3, in fact x2 with x3 star. So if I plot x2 with x3 star, now you can see that still the points are very much close to the straight line, but there are some very small or visually difficult to notice, but there are some variation. All the points are not exactly on the straight line, but very much close to the straight line. So even if I calculate the correlation between column A and column C, which is x2 and x3 star, the correlation is a very high number. It's so much close to 1. So still if I introduce x2 and x3 star as independent variable in a same regression equation, I'll be having the issue of strong multicollinearity, right? So x2 versus x3 is an issue of perfect multicollinearity, and x2 versus x3, that's an issue of strong multicollinearity. So this is what I was discussing here with the help of mathematics that I have just discussed with the help of data. So next we discuss these sort of, you can call these Venn diagram. So if y is our dependent variable and x2 and x3 are the independent variable, so it is, fairly easy to understand that if y is dependent and x2 and x3 are independent, of course that there must be some common area between y and x2. That is why we are calling that, or we are declaring that x2 is a predictor of y, right? So similarly x3 is a predictor of y because there is some common area between y and x3. But you see, there is no common area between x2 and x3. So if this is the case, it means that's the ideal scenario, that is no collinearity between the independent variables. Now if you focus on diagram B, now you see that x2 and x3, they have some points in common. So this is an issue of low collinearity, and as the common area between x2 and x3 starts increasing, we are moving towards the case of high collinearity or very high collinearity. So this is a diagrammatic depiction of no collinearity, and if you want to diagrammatically depict perfect collinearity, then of course x2 will overlap x3. So just note one other additional aspect of multicollinearity, that whenever I'm defining multicollinearity, or even if I'm trying to recheck it by calculating the correlation coefficient, then keep in mind that I am only focusing on the linear relationship among the x variable. If you revise the basics of correlation coefficient, even then you can recall that the correlation coefficient between the two variables measures only the linear relationship between those two variables. So if there is some non-linear relationship, that's not an issue, because multicollinearity states that there should not be any linear relationship between the independent variables. So if there is some non-linear relationship, that's not a problem. If you look at this regression equation, now we have a variable xi and we have the square of the same variable, cube of the same variable. So now this is not a violation of multicollinearity or no multicollinearity. In fact, we will not face the issue of multicollinearity if we run this equation 10.1.5, because x square and x cube, these are non-linear relationship, right? So now we have to let's focus that why we are worried about the issue of multicollinearity, or why do we want that there should not be any multicollinearity in the regression equation. The simple reason is that how we interpret the slope coefficient. For example, if I interpret the slope coefficient beta 1 as the partial impact of variable number 1, or variable number, I can call it variable number 1. So similarly, beta 2 is the partial impact of variable number 2 on y, and when I use the word partial impact, it means that I am holding other variables constant. Let me write something here for further clarity. Suppose that we want to run a regression equation, and let's say I say that body mass index is a function of diet, or let's say your income class as well, suppose, plus there is some residual term. Okay, so let me adjust for this typo here. Okay. So if I run a regression, a simple linear regression, and suppose by body mass index I abbreviate as BMI is equal to beta naught plus beta 1 times diet plus beta 2 times income class plus residual term. Now, how will I interpret beta 1? Beta 1 is a partial impact of diet on my body mass index. Similarly, beta 2, and when I say partial impact, it means the impact of diet on BMI while holding the impact of income class as constant. Similarly, I can interpret beta 2. But what if in a given sample, if you observe that people who belong to higher income class, they are affording a better diet, and let's say, I'm not using the word better, let's say they are affording to eat more. Of course, there are certain hypothetical conditions attached to it. It's not that richer people eat more, but hypothetically, if people who are able to afford more and they are eating more, then their BMI may be higher. So in that case, in that assumption, diet and income class will be correlated, and I can't say that beta 1 is a partial impact of diet on BMI. That is in easy word, if the independent variables are correlated, then we cannot isolate and we cannot interpret beta 1 as the partial impact of one variable while holding the other one as constant. Because if diet is dependent on income class, then there is no way I can hold income class as constant, or I can ignore the impact of income class, because if diet is changing, inherently income class is changing if they are dependent on each other. So this is the issue, or this is the reason why we don't want multicollinearity in our sample. So if there is a perfect multicollinearity, then the issue is much serious, and the regression coefficients cannot be determined, and their standard errors will be infinite, or that is their variance and standard errors will be infinite. I'll shortly show it mathematically as well. If multicollinearity is less than perfect, then the regression coefficients can be estimated, but their standard errors will be very large number, and you know that whenever standard error of a coefficient is high, it means that the accuracy or the precision of that coefficient is low. So I will shortly show here, before I discuss the reasons for multicollinearity. Let's focus here that I was just discussing that when we have perfect multicollinearity, we cannot estimate the beta. So let's have this equation. This is in deviation form, y as a function of x2 and x3, and we know that in chapter number 7 we derived the formula for beta 2 hat and beta 3 hat. So you can just quickly go and watch the video again, or you can go and refer to the chapter 7 of Gujarati and Porter Book, and you'll observe that these were the formula of beta 2 and beta 3 that we discussed there. Now if there is an issue of perfect multicollinearity, suppose if x3 is equal to lambda times x2. So now you can see x3 is a perfect linear combination of x2 because lambda is some constant. So if I substitute this value x3 in the expression for beta 2, then with certain with some minor mathematical adjustment, you can simply see that this turns out to be 0 over 0 form, that is mathematically not possible to calculate. So this is exactly what I was saying, that when we have the problem of perfect multicollinearity, then the regression betas cannot be calculated. Okay, so what if we have multicollinearity but it's not perfect? So this time, what if I add a stochastic term with the linear expression relating x3 and x2? So if I switch this value of x3 in the expression for beta 2, you will see that now we'll be able to calculate the value of beta 2 hat. So that means when we have perfect multicollinearity, the regression betas cannot be calculated, whereas in the scenario of imperfect multicollinearity, regression beta can be calculated. Okay, so coming back to the problem where we were discussing the issue of perfect multicollinearity, where I use this expression x3 is equal to lambda times x2, and we proved that the regression betas cannot be determined. So why we have not been able to find the value of regression beta, although I have already commented on it, but just a quick reinforcement of that concept. What is the practical interpretation of beta 2 hat? It gives the rate of change or partial impact in the average value of y as x2 changes by 1 unit, holding x3 constant, because remember that whenever we have more than one independent variable in the regression, then the slope coefficients are called partial impact of a particular variable. And by partial impact, I mean I am holding the other x variable as constant. But if these two variables are perfectly collinear, then it's impossible that I can hold x3 as constant. I mean, if x2 is changing and the expression relating them is perfect linear. So if x2 is changing, of course x3 will change. So I can't hold x3 as constant. So this is the reason I can't find the value of beta for the case of perfect multicollinearity. Okay, now I'll be discussing the reasons for multicollinearity. So one first reason is the data collection method. For example, if we sample over a very limited range of the values taken by the regressors, in simple words, that there is very much less variation in the values of the independent variable. For example, if in the example of BMI, and let me open that paint sheet for your ready reference. So in this example, if BMI is a function of diet and income class, so let's say if I take data in a manner that income class has very much less variation. For example, I take most of the data from the poor people or the low middle class income. So the income variation in the income data will be very much smaller. So similarly, if the diet values or the values, the range of the diet data is very small, in that case we can have the problem of multicollinearity. I will shortly show you through Excel sheet why the range of independent variable is an important thing to consider while discussing multicollinearity, right? So next is constraints on the model or in the population being sampled. For example, let's say I want to regress electricity consumption on income and house size. Now that is how electricity consumption depends upon income and house size. But if I take data in a manner that I mean people who are earning higher, they tend to have larger houses, then there will be issue of multicollinearity. And to address that, either I should try to sample those people who have higher income but still they are living in smaller house sizes, so that my data will be more generalizable or my data collection method will be better. So in a way, point number 2 is also related to point number 1. So if we have electricity, I want to run a regression in which I want to predict electricity consumption and I want to keep income and house size as independent variable, then I should take data of different type of individual, that is people with higher income still living in small houses, or maybe vice versa, people having low income still living in larger house sizes. So if I have these type of different data or respondents in my sample, then multicollinearity will not arise. But if in my data there are only that type of respondent who are earning higher and they are living in larger house sizes, of course the correlation between income and house size will be higher in that case. Third reason is model specification. Here I would like to first discuss the Excel sheet, because this polynomial term addition and point number 1 will be easily clear with the help of the Excel sheet. So let's come to this sheet, adding polynomials. Suppose this is my data. I have data independent variable, the dependent variable y, and the independent variable are x and x square. Now x square is a polynomial term of degree 2, right? So x is a simple linear term and x square is a polynomial of degree 2. Suppose that I want to check whether if I have to run a regression between y, x and x square, will I face the issue of multicollinearity or not. Now it matters what is the range of y values. If I click here, you see here I am checking the link between x and x square if x varies from 1 to 7. So you can see that the link is non-linear, but still it can be fairly approximated with the help of the straight line. I mean, the linearity or the bend or curvature is not too deep. But what if the link is checked when x varies between 1 to 5200? So if I click here, now you can see that this plot is for the full range when x varies from 1 to 5200. So now you can see that the degree of non-linearity or curvature is much higher. So what does that mean? It simply means that if we have to add a polynomial term in the regression, that is, I want to run a regression between the dependent variable y and independent variables x and x square, right? One dependent variable, two independent variable. So if I want to run this regression, I should have a look whether my x variable has a sufficient variation. So if the range of x variable is small, then adding the polynomial term will cause multicollinearity. If the range of x variable is higher, then adding the polynomial term will not cause multicollinearity. I mean, it may still cause but not strong multicollinearity issue. So this is what is meant here on the slide, that data collection method or range of the data and adding polynomial terms to the data can cause the issue of multicollinearity. The fourth reason is an overdetermined model. In simple word, if we have less data and we try to estimate more and more parameters. For example, if I have data on just 6 patients, and just with the help of data on 6 patients, and I am trying to find the determinants of, let's say, hypertension, and I want to find, let's say, what are the 10 important determinants or predictor of hypertension. Now if I have data only on 6 patients, how can I estimate 10 parameters? So if I try to estimate more parameters with the help of less data, that will also cause the issue of multicollinearity. Another reason for multicollinearity is sometimes, especially in time series data, things move in same direction. For example, the age of a son and age of father, if I follow them in 10 years, of course both of them are increasing, but I can't say that their ages are dependent on each other. It simply means their ages are dependent on time. So sometimes things move or things vary across time in similar pattern. For example, people's consumption, expenditure, income, wealth, so on, these things may vary in similar direction over time. So if I introduce these variables in a time series data, I can face the issue of multicollinearity. So these are some of the few reasons of multicollinearity. Okay, so next we are going to discuss what are the consequences of multicollinearity. Uh, Remember that multicollinearity is more of an issue of sample or behavior of the sample rather than a statistical issue. So there is one school of thought which takes the stance that multicollinearity is simply not a grave or a serious issue, and that school of thought have this justification and background that the OLS estimator, even under the multicollinearity, they still are best linear unbiased estimator or best unbiased estimator. Even if the multicollinearity is very high, as is the case of perfect multicollinearity, interestingly, the OLS estimators still retain the property of blue, that is the best linear unbiased estimator. So this is the reason that celebrated economist and econometrician, they have commented that multicollinearity is simply an issue of sample behavior. The only effect of multicollinearity is to make it hard to get coefficient estimate with small standard error. That is, the noticeable consequences or the noticeable consequence of multicollinearity is that the standard error of the regression betas, they tend to be higher. So with that it implies when the standard error is high, it means that the accuracy or the precision of the regression betas is low. So this is an issue why multicollinearity is discussed in the literature. So discussing further why multicollinearity is more of a phenomena of sample behavior. Some of the researchers have pointed out, in fact, Goldberger coined the term micronumerosity to counter the exotic polysyllabic name multicollinearity. Actually, what is micronumerosity? As the name suggests, it simply means that we have less data. So, if the sample size is small, then we have the issue of micronumerosity. If the sample size is 0, of course no estimation is possible, and that's an issue of exact micronumerosity or the counterpart of exact multicollinearity. So what is being implied or discussed here? That sometimes multicollinearity is an issue that is emerging because of micronumerosity or small sample size. So sometimes when we increase the sample size, if we can afford to do so, I mean we have the observations, we have the liberty to collect more data, then if we increase sample size, more often than not, the issue of multicollinearity is resolved. So let's discuss what are the practical consequences of multicollinearity. As we said that the regression betas remain blue, that is best linear unbiased estimator, they remain blue but they have large variance and covariances. So the issue we can't make precise estimation. So the results are less precise, less accurate, although they are best linear unbiased estimator, that the theoretical properties are met, but precise estimation is not possible. And because of point number 1, the confidence intervals tend to be much wider. So let me show you here. In general, confidence interval of a statistic, remember that statistic is a summary value calculated from the sample. So statistic can be sample mean, it can be sample median, it can be sample beta, or anything. So in general, the confidence interval for a parameter is calculated by adding and subtracting a quantity in statistic. Now what quantity is added and subtracted? It is the underlying probability distributions quantile multiplied by the standard error of the statistic. for easy example, when we construct a 95% confidence interval for population mean, you know that if the parameter is mean, then the statistic will also be mean. So the statistic in this case is sample mean, which is represented by x bar, and we know that the z value, or because the underlying probability distribution is normal, or if I talk in terms of z, then standard normal. So we know that for 95% confidence interval, the underlying probability value is 1.96. You can easily verify using the normal probability table multiplied by sigma over square root n. So what is this sigma over square root n? This is the standard error, or simply the standard deviation of sample mean. So what's the point of discussing this confidence interval here? Suppose that instead of x bar we have the confidence interval for beta. So the statistic will be beta hat. For example, if I want to make a confidence interval for slope coefficient beta 2, then the confidence interval will be beta 2 hat plus minus 1.96 times standard error of beta. So if we know that through point number 1 we just said that the variance or the standard error will be high. So if variance will be high, of course the confidence interval, or the term that is being added and subtracted, will be a large number. So confidence interval tend to be wider in that scenario. So the second consequence of multicollinearity is that the confidence intervals tend to become wider, and they are becoming wider because of the issue of multicollinearity. And when the interval becomes wider, then there is more likelihood that it will include 0 in itself. So the acceptance of zero null hypothesis increases, the chances of its acceptance increase. I will also discuss how t statistic is influenced with the help of multicollinearity, or due to multicollinearity. So we know that if we define a t statistic, it is always equal to statistic minus the test value in null hypothesis. For example, if the t stat is for beta 2, then the statistic is beta 2 hat minus the test value in h naught. So if we are testing that beta 2 is 0, then that test value is 0. So then we divide it by the standard error of statistic. So if it is for beta 2, I will divide by standard error of beta 2 hat. So that means the t statistic in the denominator, it has standard error. So if standard error is high, it's a large number or a big number due to the issue of multicollinearity, t will tend to be downward estimated or downward biased, because standard error is high, and that is high because of multi. So t statistic will be a small number. So remember that in a two-tailed test, the rejection rule is we reject h naught if t calculated is less than or equal to minus t tabulated, or if t calculated is greater than t tabulated. But now due to the problem of multicollinearity, t calculated will be downward biased, right? So h naught will not be rejected, or the results will be declared insignificant because of the issue of multicollinearity, and not because of the fact that the independent variable is not a good predictor of the dependent variable. That is, if we are testing that beta 2 is equal to 0, so the problem of the h naught is that beta 2 is 0. So if t calculated is a small number, of course the likelihood of rejecting h naught will decrease. So does that mean that due to the issue of multicollinearity, we will be declaring that the variable x2, whose coefficient is beta 2, it is insignificant, whereas in reality it may not be insignificant. It is because of the issue of multicollinearity that the t statistic is downward biased. So this is exactly in point number 3 it is written, because of consequence number 1, which is a high variance, the t ratio will become statistically insignificant because it will be downward biased. Fourth consequence is, although that the t ratio of one or more coefficient is statistically insignificant, the overall measure of goodness of fit of the model can be very high, which is counterintuitive, that the independent variables, when we check them independently, they are showing that they are not significant, meaning that they are not good predictor for the dependent variable. But once we check R square, or the overall fitness goodness of fit of the model, it says that the model is a good fit. So that means these two findings are counterintuitive, and it may be suggestive of the fact that we are facing the problem of multicollinearity. The fifth consequence will be that the OLS estimator and their standard error can be very sensitive to minor changes in the data. So the point number 5 will be clarified once I discussed a example which is related to it. So let's say this is the example. We have these two tables. If you compare table 10.3 and 10.4, you will see that there is a minor difference between these two values, these two tables. Only the third and fourth value of x2, they are interchanged, and we have generated a new table. So there is a minor difference. This is exactly written here. The only difference between table 10.3 and 10.4 is that the third and fourth values of x3 are interchanged. So you can easily verify that if I run a regression of table 10.3 treating y as the dependent variable, x2 and x3 as an independent variable, you can simply input this data in Excel, and you can notice that these results will be reported in Excel, and these the bracket values, these are the significance value or the p values. Now run the regression of table 10.4, which is simply a minor change in the data. So if I run regression using table 10.4, which I said is a minor modification of table 10.3, but you will see that such a minor modification has changed the results so much. I mean, if you compare these results, not only the coefficients are different, the p values, they have changed significantly. For example, in the last regression, if I let's say focus on the p value of x3, the p value of x3 is 0.0851. So at alpha is equal to 10%, this p value is less than 10%. So alpha equal to 10%, I can say that x3 is a significant predictor of y. But once I run the regression using table 10.4, the p value has significantly changed. Even at 10%, I cannot say that x3 is a significant predictor of y, because the p value is even greater than 10%. Usually we use the criteria of 5%, but sometimes researchers also use the criteria of alpha is equal to 10%. So here I am discussing in reference to alpha is equal to 10% criteria for p value. But the fact of the matter is just highlighting on the fact that due to the problem of multicollinearity, even if we make minor changes in the data, the results can significantly change, right? So this is one of the consequences that I was discussing. The fifth consequence is that the OLS estimator and their standard error can be sensitive to small changes in the data. Next we will discuss a concept of variance inflation factor. For the time being, even if we don't focus on these apparently complicated formulas, let's define what is VIF. Variance inflation factor, let's say if my regression is running y as a dependent variable and x2 and x3 are my independent variable, and I want to see whether x2 and x3 are they have the issue of multicollinearity. So I can calculate the variance inflation factor by using this formula 1 over 1 minus R23 square. So what is R23 square? It's simply the correlation between x2 and x3. So if I calculate VIF and it is greater than 10, then it means we have the significant issue of multicollinearity. I discussed it here as well. Suppose I have this data and I want to check whether x2 and x3 are correlated. So this is a regression in which we want to see how consumption is dependent upon income and wealth. So in this data, if I want to see whether income and wealth they have the issue of multicollinearity, or that is interdependence, although I can also calculate their correlation to check. You can see the correlation between x2 and x3 is very high number. So that also is telling us that there is the problem of multicollinearity. I can even make a scatter plot of x2 and x3, and that can also tell me where there is a linear relationship between x2 and x3. But VIF is also another criteria, which is equal to 1 over 1 minus R square, which is the correlation between x2 and x3. So by the way, here you can see that VIF is such a large number, so we definitely have the issue of multicollinearity. By the way, when we rely on different statistical software, although in this playlist or in this course we have been using only Microsoft Excel for different calculations, but as you advance through econometrics, you will also learn software like Stata or SPSS. So the good part is, if you run regression in Stata or SPSS and you opt for reporting the collinearity diagnostics as well, then the variance inflation factor is automatically calculated and reported. So if VIF is greater than 10, you can say that variable is causing the issue of multicollinearity. Okay. So next I will discuss another example. So let me focus on sheet number 6 that is mentioned here. So this is table 10.5 that we were just discussing, the correlation, dependence of consumption of income and wealth. So we are continuing with the same example, how consumption is dependent upon income and wealth. So if I run this regression, I simply ignore that there is a problem of multicollinearity and I run this regression. That is, I treat y as my dependent variable and both x2 and x3 as my independent variable. The results are reported in this sheet number 6. I have already saved them. You can run this regression afresh if you would like to. So if you look at the f value, it is a very high value. So generally a higher f value means that overall the model is a good fit. So even if you look at the p value of this f statistic, it is much lesser than 0.05. So that means that the overall the regression is significantly explaining the dependent variable. Or you can also compare this f calculated value of 92.4 with the table value. So at alpha is equal to 0.05, and at degrees of freedom you can read the degrees of freedom from this table. 2 and 7 are reported here. So at alpha is equal to 0.05 and 2, 7, you can easily check in the f table that the f value will be 4.74. So I have also shown that here. So if n1 is 2 and 2 is 7 and at alpha is equal to 0.05, the f value is 4.74. So f calculated is much larger than this or greater than 4.74. So that means that it's a significant result, and the f test is suggesting that this regression is a good regression or it's a good fit. But if I look at the independent variables p value, for example the first variable income, its p value is a high number. suggesting that this is an insignificant predictor of consumption. Similarly, wealth is also having a p-value much larger than 0.05. So it is also insignificant predictor of consumption. So this is a typical scenario of or the case of multicollinearity, that the F statistic says that the model is good. On the other hand, the independent results for the independent variable or the separate results for the independent variable, they state that they don't have any explanatory power. So that doesn't mean that consumption is not related to income and wealth, but the issue is once we showed this data here, the issue is that income and wealth, they have so much strong correlation here, that is generally in this sample people who have higher income, they are having more wealth. So this is the reason they are changing in moving in same direction. So I cannot isolate the effect of wealth as constant when income is varying. So this is the issue or a typical problem in multicollinearity. Okay, so you can try. Now you have the data. By the way, I'll share this Excel sheet with my last student. General viewers can drop me an email. I'll shortly share my email address towards the end of the video, and I can share all the Excel results or the sheets that I'm using for this video. Okay, so if I regress x3 on x2, you will see that r square of that regression will be very high, suggesting once again that x3 and x2 are highly correlated. Now if I run two different regression where I regress consumption only on income or consumption only on wealth, in both the cases the value of r square is very high, which means the separate regressions are suggesting that income is a good predictor of consumption, wealth is also a good predictor of consumption. But once we include both of them in the model, the model says that they are not a good predictor of consumption. So this is because of the issue of multicollinearity. Okay, next, although to some extent I have already hinted towards the fact how we can detect the presence of multicollinearity, but just like whenever we have a human body has some issue, then there are some indicators that represent that there is some problem. For example, if you have some chest infection, it may be depicted in your x-ray, chest x-ray. So similarly, if we have the issue of multicollinearity, there are certain indicators. For example, one of them I have already discussed, that the r square is very high. So the F statistic will say that overall the model is a good fit, but the separate p-values for the t ratios or for the independent variable, they will say that the variables are not significant. So I have just discussed that with the help of data that I showed in the Excel sheet. So one of the indicator is r square is high, F statistic has a very large value, but the p-values of different independent variables, they show that none of the variables or only a few of them are significant. Second indication of multicollinearity is high pairwise correlation among regressors. That is, for example, if we have 5 regressors in the model and I calculate correlations between these 5 regressors, for example, correlation between the first and second, first and third, first and fourth, and so on, a different pairwise correlation. So if the pairwise correlations are very high, or even if the pairwise correlations are somewhere close to 0.5, even in that case it may suggest that we have the issue of multicollinearity. Some of the researchers have also said that instead of calculating simple correlation, we should calculate pairwise partial correlations. So what is partial correlation? Partial correlation, if we have 3 variables, let me discuss here. Let's say we have 3 variables here. Suppose x1, x2 and x3 and x4, suppose. So the partial correlation between, let's say, x1 and x2 dot x3 and x4. So what does that mean? When I use the word dot, let me write it. Just a second. Yeah. So when I use the word dot here, it means I'm analyzing the correlation between x1 and x2, holding the impact of x3 and x4 as constant. So that is why I'm calling it partial correlation. In other words, I'm ignoring the influence of x3 and x4 on x1. This is the reason sometimes we want to see what is the pure influence of x2 on x1. That is why I am holding the impact of x3 and x4 as constant. So instead of calculating simple pairwise correlation, we can also calculate partial correlation coefficients. So suppose that if I have data or regression in which y is a dependent variable, x2, x3 and x4 my independent variable. So if I calculate correlation 1.234, this is simply the overall correlation of this regression. If I regress y on x2, x3 and x4, of course even if you run that in Excel, you will have the value of r square. So that r square is written as r 1.234. If this r square is very high, but the partial r square, that is, if I find the correlation between y and x2 holding the impact of x3 and x4 as constant. Similarly, the other partial correlation between one, that is y, and x3 holding the impact of x2 and x4 as constant. These are all low number, but overall the model has a high r square value. This is another indication that we have the problem of multicollinearity. Fourth is a check through auxiliary regression. Auxiliary regression simply means that we can regress one independent variable on the remaining. For example, if in our model we have three independent variable, x2, x3 and x4, so I can regress x2 on the other independent variable, then x3 on the remaining independent variable, and then x4 on the remaining independent variable. So these are my auxiliary regressions. So how do we use the auxiliary regression output to comment whether we have the problem of multicollinearity or not? First of all, we note the value of all auxiliary r square value, and we compare it with the original r square. That is the case where y is regressed upon all independent variables, in this case x2, x3 and x4. So I will compare the overall r square with the auxiliary r square value. So let me clarify once again. Auxiliary regression is if we have three independent variables, suppose x2, x3 and x4, I will regress x2 on the other two independent variable, then x3 on the remaining independent variable, and similarly x4. So we will have three auxiliary regressions. So when we run three auxiliary regression, we will have three values of r square or the auxiliary r square. So if the value of auxiliary r square is greater than overall r square, for example, if the value of auxiliary r square of x2, right, if that is high, let me explain once again in Excel. Suppose this is the data, and in fact let me make a new file here, sheet here, because I want to discuss more than two independent variables. So if suppose this is my dependent variable, then these are my independent variable, right? And we will have let's say I'm just hypothetically inputting any data here. suppose I want to see whether if there is any problem of multicollinearity if I include all the x's in the regression. So first of all, I will run a regression of y on all the x variables. So you know that I can do that by clicking on data analysis and then choosing regression here. So my y range is this and x range is all of these variables. So I can save it in new worksheet file. So that's saved here in sheet number 4, and the r square value is 0.9971. So this is my r square value. So this is the value of overall r square. Similarly, now I will calculate the value of auxiliary r square. So for now I am deleting this sheet because I just want to explain with the help of this data. Now how you will find the auxiliary r square? Suppose you want to see whether x2 is causing the problem of multicollinearity or not. What you will do? You will regress, that is you will treat x2 as your dependent variable and x3 and x4 as your independent variable. So once you run this regression, you will also have a value of r square. So that will be auxiliary r square for x2. So if auxiliary r square is greater than the overall r square that we just noticed, then it means that x2 is causing the problem of multicollinearity. So this is what is being discussed here. I've already discussed the variance inflation factor. Remember that the different methods that we have discussed to detect the problem of multicollinearity, they all have their own weaknesses, and in a given sample we should not rely only on one method. We should try to check multicollinearity using more than one method so that we can confidently state that we have the problem before we try to resolve the issue of multicollinearity. So different remedial measures are proposed to resolve multicollinearity. One of them is to use a priori information that relates different parameters in the regression equation. For example, if we want to regress consumption on income and wealth, and suppose that somehow we know that beta 3 is equal to 0.1 times beta 2. If we somehow know this, then we can switch this value in the original equation and we can reduce the original model into this abridged or the shorter version of the model. So now if I calculate beta 2 by running the regression of y on xi, where xi is equal to x2i plus 0.1 times x3. So I am going to calculate a new variable xi with the help of x2 and x3, and I will run regression of y on xi. So I will calculate this coefficient. So once I have the value of beta 2 hat, I can easily find the value of beta 3 because I can simply put the estimated value of beta 2 hat to get estimated value of beta 3 hat in this equation. But the problem is, where do we get this equation from? I mean, this type of a relationship. How do we know which relationship holds? So most of the time, these type of relationships are guided by the underlying theory. For example, recall the Cobb-Douglas production function that relates the output or GDP in an economy with the labor input and capital input. So we know that if there are constant return to scale, then beta 2 plus beta 3 is equal to 1. So if we impose this restriction, we discussed it in chapter 7. You can watch that video again, that this model is reduced to 8.6.8 form, where we simply switched value of beta 2 equal to 1 minus beta 3, and we solve it a bit to get the regression equation in output labor ratio and capital labor ratio form. So now instead of running the original regression, I can run this regression, and I can always test whether the restriction that I have imposed, if that restriction is correct or not. So we can test the validity of such restriction that we discussed in video number 14. of this playlist, so you can go and watch again. So the point is, if we have an a priori expected relationship between the parameters, we can impose that in the model, and we can then run the transformed model, and then we won't have the problem of multicollinearity, and we can check the a priori relationship between the parameters with the help of a procedure that is discussed in video number 14, where we discussed how to test linear restrictions on parameters. Another remedial measure is to drop a variable. I mean, if one variable is causing issue of multicollinearity, for example, if we see that consumption is dependent upon income and wealth, but income and wealth, they in turn are dependent on each other, so we can drop one of the variables from the model. However, this approach in itself has its issue, because if we drop a variable which is very important, then we are committing another error, which is called specification bias or specification error. In short, if we drop an important variable from the model just to resolve the issue of multicollinearity, then even then sometimes the results are not reliable. We cannot directly interpret them. So although I haven't discussed specification bias directly in this playlist, but for that you need to read the later chapters of the book. For now, you can understand that if we drop an important variable from the model, that also badly influence the regression results. So that means that dropping a variable, especially if it's an important variable, theory will guide you. For example, the theory say that consumption and the important predictors of consumption are income and wealth. So the theory is saying that these predictors are important. So just to resolve the issue of multicollinearity, I should not drop one of those variables. Another approach is to transform the variable. One of the transformation is called the difference transformation. This is especially true if we have time series data. So if we have time series data on the variable, we can simply calculate difference between current observation and previous observation. For example, if yt stands for the value of y in year 2000 and yt minus 1 stands for the observation of y in year 1999, then I can calculate these differences. So all the x variables are also in difference form. So the importance of this difference form is not only it resolves the issue of multicollinearity, it also often resolves the issue of non-stationarity, which is a frequent issue in time series. Similarly, in some cases we can also apply a ratio transformation, where we can divide all the variables by one of the independent variables, so that we are able to express the ratios instead of original variables. So this is sort of a hit and trial method. I mean, you can try the ratio transformation or the difference transformation, and you can check whether the multicollinearity issue is resolved or not. I mean, you can now calculate the variance inflation factor of this equation, and you can check whether ratio transformation has resolved the issue of multicollinearity or not. But you also need to take care of the fact that apart from multicollinearity, there are other important assumptions of OLS. So while resolving multicollinearity, we should also check whether we have not invited the issue of autocorrelation or heteroscedasticity. So we will in upcoming videos we will discuss in detail the problem of autocorrelation and hetero. So for now, it's in simple words, while resolving the problem of multicollinearity, we should check whether we are inviting other problems in the model or not. Okay, so another important and I would say an ideal remedial measure for multicollinearity is if we can afford to collect more data, include more data in the sample, we should do that. I mean, when we were discussing the relationship between consumption and income and wealth. So generally we saw that people, if I just make a scatter plot here, then you will be able to. So now you can see Generally, people those who are earning more, they have more wealth, because we have an upward sloping diagram here. But if we try to include more respondents in this sample in a manner that some of those respondents are including who are earning higher, still they have low wealth, or vice versa, people who are earning low, still they have more wealth. If I include those type of respondents in the model, so actually I am trying to include additional or new data. So in that case, the issue of collinearity will be resolved. But of course, it's not always easy to collect or to include more data, but this is one of the ideal solutions for multicollinearity. There are other important or algebraic solutions to multicollinearity, like factor analysis or principal component or even rich regression, but they are not included in the scope of this course, because these require a fair understanding of matrix algebra, which generally is discussed in advanced courses of econometrics. Anyhow, so now we will be doing a couple of chapter exercises. This is exercise number 2. Suppose we have data on these 3 variables. Can you estimate the 3 unknowns? I mean, I want to regress y on x2 and x3. So can we estimate? So let's see if I have this data on. I've saved it here in question 10.2. So this is the same data is copied here. What I have done is, you see x2 and x3, if they have multicollinearity and if that's perfect, then we cannot calculate. So when I made the plot between x2 and x3, you can see that we have the issue of perfect multicollinearity. So that means we cannot calculate, because x3 is a linear combination. And if you have a close look at data, you can easily verify that x3 is equal to 2 times x2 minus 1. So if I substitute this value of x3 equal to 2 times x2 minus 1 in the original regression equation, I can simply transform this model into its reduced form. Now I can estimate alpha 1 and alpha 2, but I cannot estimate beta 1, beta 2 and beta 3 uniquely. Next we have question 10.3. This is in reference to the child mortality example that we discussed in chapter 8, but don't worry, I'll show that output once again. So let's say, let me show you the original model. In the original form, child mortality was regressed upon per capita GNP and female literacy rate. So if we include an additional variable in the model, right, now we are regressing child mortality on per capita GNP, female literacy rate and total fertility rate. So this is the regression output. Now the question is, we have to compare these regression where with the original regression where TFR was not included. So if you look at these variables, per capita GNP negatively influence child mortality, that is, if per capita GNP of a country increases, child mortality incident is expected to decrease. Similarly, if females are literate, child mortality is expected to decrease. If the total fertility rate is higher, child mortality rate is expected to increase. So these are the key results from these. The original regression equation, if you look, without the TFR form, which is 8.1.4, so you can see that not the numerical values, they have changed. I mean, I have copied this here again. If you compare the intercept has changed. Similarly, the coefficient of per capita GNP and female literacy, both have changed, but still the signs are same. I mean, their signs have not changed. So and if I look at the significance, the p-value here in the new regression, per capita GNP and female literacy rate, they are significant, whereas in the later model, female literacy rate was insignificant. So you see, just by adding a new variable, the significance value of the pre-existing variables, they can change. If, for example, I talk about female literacy rate, in the original model it is insignificant because p-value is very high, but once we include TFR, its p-value becomes smaller, and now it's saying that female literacy is a significant predictor of child mortality. So these changes are due to the addition of the new variable total fertility rate, suggesting that there may be some collinearity among the regressors. Part B is it worth adding the variable total fertility to the model, and why? So I have just discussed that the p-value of total fertility rate is significant. So that means that TFR is a significant predictor of child mortality. The positive sign of this coefficient is also in congruence with the theory, which is implying that larger the number of children born to a woman, the greater the chances of increased child mortality. So we should include TFR in the model. Part C is, since all the individual T coefficients are statistically significant, can we say that we do not have a collinearity problem? Because we said that generally when we have multicollinearity issue, then the p-values or the T statistics are statistically insignificant. But this is one of those rare cases where even in the presence of multicollinearity, the individual coefficients are statistically significant. So you can try these exercises from the chapter to develop further understanding of the issue of multicollinearity and how it is discussed in different scenarios. So thank you for watching this video. Once again, a humble request to subscribe to the channel, like the videos, and develop a professional connection with your instructor. So best of luck from Dr. Aisha Nazok, and keep learning, keep watching the videos.